Okay, now we're on part three, a short one on Parseval's theorem, which is really, I'm actually just going to go through what's described there in the chapter for Parseval's theorem. And Parseval's theorem, the point is to relate energy to the Fourier transform. How much energy is carried in the Fourier transform? And I can tell you from my time in communications, this is really important in how communications work, because communications involve the transfer at frequencies or a range of frequencies, a spectrum of frequencies, either over the air, over wires, over fiber optics, all kinds of means of transporting a mix of frequencies. But the thing that makes the whole process work and effective is that energy is being transferred and Parseval's theorem helps us quantify that or qualify that. So let's if I can get this to work. Whoops. So this is the simple, let's integrate power over all time. The power of time, P of t, that's the power in some signal. This is not Fourier transform or anything yet. This is just the statement of work. That's energy. This is just a statement of what your electric bill looks like. Power is watts in your electric bill. Work or energy is watt hours. How many hours did those watts get drawn? You pay for watt hours. You pay here for the thing on the left. This is the dollars over here. This is the rate at which you're drawing power. This is a rate. Right? Okay. So it was noted, and this is Parseval's note, that if I take the amount of energy, right, in a 1 ohm resistor. So kind of what this is saying is we know up here from this power is equal to volts times current. Oh, but we use Ohm's law and we get that it's volts squared over R. Or we can say that it's current squared times R. And the point of the 1 ohm resistor is if this goes to 1, the resistor, we really are just talking about volts squared or current squared. Okay? So that's the simple thing that we're going to use to lever from time to frequency. Okay? And so let's do that. I can just copy what is in the text. We have this, by the way. This whole formula becomes this. And if you take a look at, I'll just reference in your text. Let's see. I've got whatever page it's on, but it's equation 18.8 in the text. Really shows you, what does it show you? That the frequency transform, right? I'll put enough of it here that you can see. The frequency transform, which is the Fourier transform of f of t, bad thing there, of f of t, right? So now we're in the range of this p of t here, and this f of t, the Fourier transform of that, is equal to this integral of f of t. This is just definition, right, over all time, of the integral of f of t e to the minus, so f of t e to the minus j omega t dt. Okay? And if if I want to know the time over all time, I want to know for negative, then it becomes, right, a minus omega. So f of minus omega, I can speed this up. I just plug in minus omega, so that's going to be the integral minus infinity to infinity of f of t e to the j omega t dt. Okay? So when I do that, I now have the way to account for both plus and minus omega, the full spectrum of time, and we're going to need that. We're going to need that in a little bit here. Okay? So Parseval's theorem specifically will go on to say this, that the total energy delivered to a 1 ohm resistor equals the total area under the square of f of t, or 1 over 2 pi times the total area under the square of the magnitude of the Fourier transform. That's what's going on here. Here's the magnitude of the Fourier transform, and if you take the magnitude, there's the magnitude bars. Take the magnitude of the Fourier transform, square it, but you integrate all the area under it, right? So it's 1 over 2 pi times that. If you follow through back in the text from 18.8, you'll see when you finish that, you end up with a 1 over f of t. The transform of that is 1 over 2 pi. Maybe I can write it in here. F of t is equal to the 1 over 2 pi, 1 over 2 pi, if you're just wondering where this 2 pi comes in, of the integral of minus infinity to infinity of f of w, right? E to the minus e to the j omega t dw now. Okay? So that's our transform, and that's all that's going on here. That's where the 1 over 2 pi is coming from, the f of omega. Now, if I had f of t squared, I plug in f of t squared, I'm going to be dealing with 1 over 2 pi magnitude f of omega squared. E to the j omega t is going to disappear because I'll have the two kinds, omega and minus omega, because I'm covering all of the space. So I'll have minus j omega t and plus j omega t. Okay? All right. Let's go back and work on this a little bit then. So here's Parseval's theorem for the 1 ohm resistor. We already saw this. This is our f of t. Okay? And it's f squared of t right here, right? F squared. So I'm going to break this up into two parts. So here I just sort of stretched out one portion, f of t dt, right? Now I'm going to substitute back in the Fourier transform, right? So I just showed you this. This is equation 18.9. That's this thing right here. For one f of t. All right, so what have I done now? I've taken the basic definition, and I've said I'm going to integrate a single f of t, and I'm going to substitute the Fourier transform for the other f of t. Plug that in. So now I'm going to have an integration in terms of dt and another one in terms of frequency. Okay? So let's see what kind of trouble this gets us into. So here is that same thing. Now I've just factored out the constant. Here's that. And now I'm just pulled out the constant and said, okay, now I've just got two integrals. One, I haven't actually changed anything. I just got rid of these brackets, and moved out the constant. So now we can see more clearly I've got one integral buried inside another, but they are integrals of two separate variables. Okay? And if we keep extending this, we can say, oh, what's my next step? Well, all I'm doing is manipulating here now. I'm not actually performing any mathematics. This was simple substitution. Okay, this is just moving terms around, collecting terms. Okay, ordering terms. I don't know how you want to say it. Okay. And now I'm actually reordering terms. Okay, so I have an integration in terms of t buried inside an integration in terms of w, frequency, okay? But this just says, oh, but now look, I recognize this thing as this thing, right? This was just equation 18.8, equation 18.9 for minus f of minus w, right? I can go back, let's see, can I zip back to that stuff? Maybe I got enough of it there. See, here we are here. When I plug in minus omega, yeah, I'm right here, minus omega, right? That's, I'll fill this back in. That's where I'm at here. Well, in fact, it's already written here. Here's what happened. I took f of t, right, and I said minus j omega and j omega, right, and now it's a j of minus omega, so the Fourier transform just puts the minus sign here, right? I had e to the j omega t, that's equation 18.8, right? I had e to the j omega t, and now I say, but I want to work in minus omega, so it's e to the minus j minus omega t. It's still the same thing, and that's, oh, now I'm working in minus omega. Okay? That's what's going on there. It's just substitution and reordering terms. But you had to catch this little plug-in right here. This, the minus signs, a minus times a minus equals a plus. And what happened is we worked it backwards. We said I started with a plus. I want one of them to be minus, so now I have to make the other one a minus, right? And then, oh, lo and behold, when I do that, I end up with the Fourier transform of a minus frequency. All right, so what is this? This is now, I'm saying this is this term, which is the conjugate. So Parseval's theorem now is coming down to some kind of basic stuff. If I have the Fourier transform and have or can make the conjugate of the Fourier transform, I can readily get to the power and the work. Okay, so let's take a moment and refresh ourselves what's going on here, right? I'm not assuming that's okay. So let's take a look. Let's just z and x and y. This is not x an input and y an output of a box or anything. This is an aside. on complex conjugates. Okay, so this is a complex number, right? Z, x plus jy. If I have Z conjugate, product of those two, here's Z, and we know the conjugate is this. Okay, so now let's just go about multiplying them out. X times x is x squared. X times minus jy. So this is what? X squared minus jxy plus jxy minus j squared y squared. Okay? Well, these two disappear. This goes and makes that a plus, and we get x squared plus y squared. That's all this is saying here. And that is equal to the magnitude of z squared. Okay? Sort of looks a little like Pythagorean theorem there, doesn't it? Or that sort of thing. If I have a triangle, a right triangle, and I had x and y and z, we know this formula holds. Okay? So all I'm doing is the complex numbers there like that. So I get z squared, the magnitude of it, the length of this bar, whether y is positive or negative or x is positive or negative. This is always going to end up as a magnitude, right? Why? Because if x is negative, the square, this is always going to be a positive number. This is always going to be a positive number, no matter how they started. Okay? So, back to our original problem of the work in a 1 ohm is the function squared. This is just repeating what we've had earlier in the process. And so now it just says, look, here we are. We're substituting f of omega, the magnitude squared. So that's like this, right? So if we plumb all that backwards, right? If we plumb all that backwards, we're saying this whole thing is now just equal to that whole thing, right? What happened here? Whoa, this whole thing, that whole thing. Here's the observation. This, right, this is the same as this. Right, those are equal. What happened here? Our number 2 went away, but we also changed the limit on the bottom. And the change that went on here was we noticed that the square of things, right, makes everything positive. So all I have to do is integrate over the positive axis from 0 to infinity, and that's equal to twice the integral from minus infinity to infinity. Okay? And so that's what happened here. This just said this alone is equal to 1/2, but I need 2 of those, right? So I double that, and that cancels out the 2. Okay, so that's what's going on with that guy. And you can also, by the way, take this, and we do this a lot in communications. No one says you have to go all the way from 0 to infinity. You could take a bandwidth here. And accomplish the same thing. Okay? So a whole lot of derivation and math and stuff, but look what happened. We're able to get the amount of energy expended from, and we were able to get this from the transform. A really good application of that. Okay? And that's what I'll say about Parseval's theorem. More a derivation than anything at this point, but the usefulness of it is a lot in communications.